Good day and welcome back to the second installment dealing with vector valued functions. So in the previous video, we introduced the idea of a vector valued function, followed up with some of its kind of common properties. And we culminated that video by introducing the concept of a space curve, just the idea that one of these vector valued functions will trace out some curve in three-dimensional space as we let that parameter value t vary. So kind of as a reminder, this r of t that we see is one of these so-called vector valued functions. And if you prefer, you can also think of this component-wise opposed to writing it out in terms of those standard basis vectors. So those are equivalent representations of this vector valued function. Now, in order to sketch this space curve, which is going to be a familiar question, we need to really break it down into considering those parametric equations. So in this case, we have the x, the first component, is made up of cosine. Y, the second component, is sine. And the third component is t. And we would refer to these as being the parametric equations for the space curve. And in order to sketch a space curve, i.e. put these parametric equations to use, we need to think back to maybe the end of Calculus 2. At the end of our Calculus 2 course, we were dealing with parametric equations, in the plane. So we just had an x and a y. So now it's really taking into account this third coordinate as well. And what we typically want to do is look for some relationship between these functions that we can exploit to get a relationship between the x, the y, and the z. And whenever we're dealing with trig functions like sine and cosine, there should be something that jumps out to us. Note in this case, x squared plus y squared would be cosine squared plus sine squared, which by the Pythagorean identity is 1. So what that is telling us is that this space curve lies on the cylinder or the surface given by x squared plus y squared equals 1. So right away that gives us an idea or a frame to work with. So let me go ahead and get this into the picture. So the curve lies on the cylinder given by x squared plus y squared equals 1. And this is an example that we encountered at the beginning or first video of the 12.6 material. Where in this case, the circle that we have in this z equals 0 plane is that unit circle. So it intercepts the x-axis and the y-axis at 1. Now, we know the curve lies on this cylinder. The question is, what can we do to further restrict that, to understand it? And this is where this third z coordinate comes into play. So we can think of the x and the y coordinate as kind of restricting us to this cylinder. The z coordinate is going to determine the height or the position on that cylinder. So let me go ahead and just make an observation. So since z is equal to t, the curve will spiral around in the upward direction as t increases. So let me get a simple kind of starting point. If t is equal to 0, we have the point given by cosine 0, sine 0, and 0. So at time 0, we're starting off precisely at that point 1, 0, 0. And as we let t vary, cosine and sine just moves around the z-axis. This is actually a parametric description of the unit circle. But the t is going to give us height as we rotate around. So as t increases and we rotate around, we are slowly going to increase in height. And then as t decreases, we would wrap around the cylinder, but we'd be going in that downward direction. And because of its shape and its spiraling behavior, this is something which is called a helix. And I realize there's something that's difficult about taking parametric equations, especially now that we have 3 dimensions, and getting a space curve out of it. And one thing that can really help is seeing it in a computer program, so a better animation than I can possibly provide here on the screen. And that completes our first example of sketching a space curve. And note the key observation or thing we needed to do was exploit this relationship between several of those parametric functions to come up with an idea of how to get started. To get a little more geometric intuition, we are going to turn to Geogebra for some help. So I have this little pre-recorded video that I'm just going to talk over. In red, what we see is the cylinder x squared plus y squared equals 1. So the x-axis in red, the y-axis in green, the z-axis is blue. And we said that the helix is going to wrap around this blue or z-axis, and it's going to live on this cylinder. And here we see that helix as that black curve which wraps around the cylinder. And just to give you an idea of how that parameter value varies, we have A as a point on it, and as we let t, the parameter, increase, we will see that that point is going to wrap around the cylinder in that upward kind of positive direction. And once again, this is just a small animation created using Geogebra, which is a freely available program that I recommend you all take a look at to help visualize 3 dimensions. Now, what I'm going to ask you to do now is exactly what I would ask you to do if we were in class at this point. I'm going to give you another vector valued function, and this is actually very familiar to us. It's something that we've recently encountered. And what I would like you to do is identify what this curve is, maybe give a short description, and then based upon that description, do your best to sketch it as well. So pause the video and take 4 or 5 minutes. Okay, so assuming that you've done that now, the parametric equations given by this vector valued function would be x is equal to 1 plus t, y is equal to 3t, and z is equal to minus t. And this is something that if I was to have presented it to you a few sections ago, you hopefully would have immediately shouted out to me what this represents. These are the parametric equations of a line. So this would represent a line, and remember, a line is determined by 2 quantities, a point and a direction. And as a really quick reminder, if you have the parametric equations of a line, x equals x naught plus at, y equals y naught plus bt, z equals z naught plus ct, we can very quickly identify the point and the direction vector. So in our case, the point will be given by those numbers, which are in front of the t quantities. So the point that we go through would be 1, 0, 0, and it goes in the direction v, which is given by the coefficients respectively of t in the x, the y, and the z parametric equations. So with this in mind, we can probably give at least a rough sketch. And remember, as I've mentioned multiple times, our pictures do not need to be perfect. Far from it. We're not going to be graded on our artistic abilities, which is good for me. But we just need to get that main point across. So we're looking at the line which goes through the point 1, 0, 0. in the direction 1, 3, minus 1. So what I want to do is think if I'm at this point, 1, 0, 0, what does it look like to move to 1, 3, minus 1? So I go 1 in the x direction, 3 over in the y direction, and 1 unit down. So about right there. So see if I get it right. And if we're at 1, 0, 0 and we move in that direction, we end up at the point 2, 3, minus 1. So somehow I just want to draw a reasonable looking line connecting those 2 points. And just to make sure we're all on the same page, this vector joining the 2 points would be the direction vector v. So 1, 3, minus 1. So now, once again, the key observation was that we somehow knew what this curve would look like. So for now, the curves that I might expect you to be able to recognize would be lines and helixes. And furthermore, I would strongly encourage you, as usual, to make sure that you're looking at suggested problems in the book so that you can become familiar with other common examples. The next video, we will look at some of the common types of questions that we might be asked beyond just sketching a space curve. So stay tuned and take care.